Annenberg Media.
Why can't I see colors in a dark room?
Why can't I see anything if there isn't any light?
Do all animals change color?
Welcome to Shedding Light on Science. I'm Anita Greenwood, a science educator at the University of Massachusetts Lowell.
And I'm Christine Jones, an astrophysicist at the Harvard-Smithsonian Center for Astrophysics. Later in today's session, we'll be joined by our colleague, Dr. Camille Wainwright at Pacific University. In this series, we've seen that light is made of photons of differing amounts of energy. In Workshop 3, we talked about visible light, as well as light that's not visible to us. We looked at how we detect light that we can't see, like radio photons that open garage doors, and infrared photons that we feel as heat on our skin. And I talked to you about my work with X-ray telescopes.
Today, we'll focus on detectors that are familiar to all of us, our eyes. You may not usually refer to your eyes as detectors, but that's exactly their function, to detect the presence of visible light energy.
Compared to the whole spectrum of light, the region that our eyes can detect, the visible light region, is quite small. It's the interaction between visible light, our eyes, and our brain that we'll explore today.
Let's begin by examining how children believe we see objects. We asked Michelle Sullivan's 4th grade children in Worcester, Massachusetts, to draw posters to explain how they think they see objects. How do you think children in your class would explain how they might see a tree in a field?
Here's my poster, and it shows this little boy reading a book, and he's thinking about what he said, like that he couldn't see without light. And this boy is trying to figure out a math problem, and it shows him looking at the object, it coming back into his brain upside down, and then projecting out again upside down, right side up. And over here it says facts. It means 5 actual causes to seeing. All the colors you see come from 3 colors: red, blue, and yellow. Number 2 is light is a different color. Number 4 is you see from light. Number 5 is light makes colors.
The light entered to our eyes, but it doesn't enter correctly. The picture that we are seeing enters upside down, and then it goes after in our head, and then it skims again correctly, and so we can see. Here read that we can't see without light, and we can't see the colors in a dark room because there is no light. That light is an important resource for the Earth.
I drew a car, and I have an eye looking at it, and these are seeing lines, but you don't, like, when you're looking at something, it does, if someone's looking at you, they don't see seeing lines. it's invisible. And I said they're looking at the car, and I wrote, seeing lines are colored light that we can see right away. And in the air, there are colored particles that help us see the light and color. And it helps us see because if we don't have any light, then we couldn't see anything. Well, a lot of people think we can see in the dark, but all we will see is black and white, and we need like either seeing lines or something to see or hear or like look at something.
This is the room where the light is on, and this is the room where the light isn't on. And over here it says you can only see black and white when it's dark. And here you can see colors when the light is on.
How we see is we use light because we can't see without light. And here the sun is reflecting toward the eye, off the eye, and the eye sees by looking at the tree. And then inside here, it's upside down and then reflects back out, and you see it right side up. And down here I'm seeing the eye sees by looking at the tree with help by the sun for light.
This is the sun, and these are light rays. The light rays are going at the tree, and then the light's bouncing off the tree. It's going into the eye like this. Then these light lines cross, making the tree look upside down at the back of the eye, which is called the retina. The retina has a nerve that's connected to the back of the brain, and the brain tells you which way the tree should be and how far it is, and it makes you see it good. And without light, you can't see anything because the light needs to bounce on an object, so it can go into your eye and into the back of the brain.
What I drew was, for an example, I drew a fish for the picture, and the sun is reflecting on the fish because I drew a little key here. It's like, this is kind of like a web here, and like the yellow one means sun reflection, and the red one means reflection to the eye. That means the reflection is going into the eye. I wrote sun reflects on the picture, so it's reflecting off of the fish and it's going into the eye. The picture goes through nerves to the back of the brain, and I put a dot where it goes to, and you see it upside down, so it flips it right side. This is what it's showing it's doing. Flips it right side up, so your brain sees it as right side up.
Let's take a closer look at their posters. All the children said that we need light to see, but they didn't always make that connection in their poster. John imagines vision as looking out and then getting light back from the object. Crystal has the idea that the light from the sun goes to the eye and then from the eye to the tree. Shane uses the idea of seeing lines, which seem to come from the eye almost like Superman's invisible rays. These seeing lines let us see objects. He also includes an interesting idea that air has coloured particles in it that we see in the day. Deborah, Erin, and Chris clearly show that light from the sun is reflected from an object to our eyes. These children hold typical ideas of vision similar to early scientists.
In the year 965 AD, mathematician and physicist Alhazen was born in Basra, presently Iraq. In his lifetime, he created a new understanding of how we see. Prior to Alhazen, people believed our eyes emitted rays that made objects visible. He observed that when looking at light, such as fire or the sun, his eye would feel discomfort. This proved that the eye is affected by light. Alhazen also showed how light affects sight. If he was in a chamber with a wide opening exposed to the sky and light and looked at the opening for a while, he would find the shape of the opening remained if he closed his eyes or turned to a dark place. With these two experiments, Alhazen showed the relationship between light and what we see. Because of this and other extensive research, he is considered the father of modern optics.
Our colleague, Dr. Camille Wainwright, a science educator at Pacific University in Oregon, showed us a model of an eye that she uses with her students.
Eyes. We all know something about them. They have lids and eyelashes to maintain and protect the eye. In conjunction with the tear ducts, they keep our eyes safe, clean, and moist. They wipe away dust and tears, similar to a windshield wiper. Another thing we can see is the color of the eye on the front of the white eyeball. The color portion of the eye is called the iris, and it comes in various shades of blue, green, gray, hazel, or brown. Regardless of the color, eyes have a black spot in the center of the iris. This is the hole through which the light enters the eye, the pupil. The cornea is the first optical component of the eye. The light is refracted as it passes through the cornea. The path of light continues through the pupil and then through the lens. When the light meets the lens, it is refracted further. It changes direction as it meets the front surface of the lens and refracts even more as it leaves the back surface of the lens. The lens in the human eye is remarkable. It actually changes thickness in order to focus the path of light. When you're looking at something near to your eyes, your lens must be very thick in order to focus the image properly on the retina. When you look at something at a distance, muscles pull the lens thinner so that you can focus on something far away. This is a very realistic view of the retina because we can see the blood vessels, which resemble the branches of a tree. We can see the fovea, which is the place on the retina where we have the sharpest vision. Notice there are no blood vessels in this area of the retina, but there is a concentration of detectors here. At this spot, there are many blood vessels, but no detectors. That's why this is called the blind spot. This is the place where the nerves collect into a single bundle called the optic nerve. It's the optic nerve which carries the vision message from the retina to the brain. We'll be looking at the function of the parts of the eye in more detail throughout this workshop.
Let's look at our own eyes now. If you're alone, look in a mirror. If you're in a group, pair up to do this activity. Look closely at the iris and the pupil of your partner's eyes. Or look at your own eyes in a mirror. Now cover one eye and notice what happens to the pupil in the uncovered eye. If the pupil is just a hole, how does it change when you cover one eye? Why does it change when you cover one eye? What other function might the pupil have in helping us see?
good analogy to the eye is a camera. The camera has a diaphragm which changes the size of the aperture, the hole in the front of the camera that the light passes through. This is like the iris in the eye, which changes the size of the pupil. Here we can see the diaphragm changing. When we want to photograph to show everything in focus, objects near as well as objects in the distance, we need a very small aperture. If we want to take a photograph of an object close to us, and we want that object in focus, but don't want the background in focus, the opening in the diaphragm must be large. We are talking about depth of field, the range of distance that is in focus. In the eye, the pupil changes size, not only to control the amount of light that comes in, but also to control the depth of field. The camera lens refracts the light so that the image can be focused. However, the camera lens is not flexible like the lens in the human eye. The image must be focused at the back of the camera where the film is located. The film absorbs the light energy, which is transformed to chemical energy. We've seen that the camera has some similarities to the eye, but the eye is much more complex. I visited Dr. Carl Sitek, a professor of optometry at Pacific University, for my yearly eye exam, and he took a close look at my eyes.
Can you see anything on the line below that?
It's a little fuzzy. ZKCZV.
Great. And now with both eyes, please.
ZKCSV.
Excellent. We did that as a test of your ability to see fine details. Okay. Now I'm going to check your eye movements. Do you see the little letter A right there?
Mm-hmm.
Okay. And just follow it with your eyes. Keep your head still and just move your eyes. We need to move our eyes because that area of the retina that has the clearest vision is only a very small part. So if we want to look at fine details, we need to move our eyes around. And we have to check that to make sure that you can move your eyes in all directions. Okay. I'd like you to look out at the distance, please. And here I'm going to check that your pupils are responding properly to light. Now the reason that we do that is to check that the pupils constrict and dilate properly. Now they do respond to light to control the amount of light that gets into the eye, but that's not the main reason why they work. The pupils control the depth of field of the eye, and what that does is it gives you a range of clear vision. So it allows you to see near and far without having to change focus.
So on one of my cameras, I have the ability to change the diaphragm to allow me a larger range of distance in which I can focus.
Yes, that's correct. It works exactly the same way. Okay, that was very good. Now we're going to check the health of the eyes with this instrument. And I'd like you to put your chin on the chin rest right there. And hold real still. I'm going to be videotaping this for later so we can take a look at it later. So the first things that we'll look at are the optical components of the eye. In the front we have the cornea, which is the clear window where all the light comes in. It actually changes the direction of the light, and it is the strongest of the optical components within the eye. And on the right-hand side of the image, we see the right part of the curved slit, and that represents the front surface of the cornea. Just to the left of that is the back surface of the cornea, and that's represented by that second curvature. The next component then is the lens. And the lens sits behind the iris, which is the colored part of the eye. That also makes the pupil of the eye. Now the lens has a front surface, which causes the light to change direction even more, and it also has a back surface. Now when we look from something far away to something close up, the lens actually changes thickness, so the focus of the eye changes. As we get older, the lens thickness increases, and we lose the ability to change the shape of the lens so that we can no longer focus from far to near. Now we're going to check the lens powers to make sure that we have the best possible correction for the glasses that we may be prescribing. We'll check the right eye first. So what I'd like you to do first is read the lowest line on the chart that you can.
DVOHC.
Very good. Now we're going to check the final refraction. I've got one line of letters out there. I'd like you to read that as soon as you can see them, even if they still look a little bit blurry.
I can see them now.
Good. Try for me, please.
HVZDS.
Good. Does that look any better?
A little bit.
Okay. And what if I go one more step?
That's better.
Great. Okay, we'll hold it right there. Now I'm going to take a look at the back of the eye. And to do that, I need this additional lens to help focus the light more. So here we're looking at the retina, and I can actually see the fovea, which is the area of the clearest vision. And if you remember before when we tested eye movements, when you were doing the tracking, that's the part of the eye that you have to move around to be able to see clearly. We can also see the blood vessels, and those blood vessels actually lie on top of the photoreceptors. And here we have the optic nerve head, which makes up the blind spot of the eye.
Here's another representation of the human eye. This model has some useful features that allow us to demonstrate the way an image is actually formed. At the front, the glass represents the cornea. I can add a part that represents the iris with the pupil in the center. Then I'll add a lens. And finally, water with dye in it to represent the liquid which fills the human eye. Although the liquid in the eye is a much more complex solution than water. In the front of the eye is a source of light. We can see the image formed on the back of the model, the area that represents the retina. Notice that the arrow in the light source points upwards, but the arrow on the image is inverted. We can clearly see the image on this model, but if we looked inside a human eye, we would not see an image sitting on the retina. That's because the retina has absorbed the image. It has literally soaked up light energy and converted it into the chemical energy and the electrical energy that carry the message to the brain through the optic nerve. In the human eye, the thickness of the flexible lens can be adjusted to focus light on the retina. But if the lens can't adjust sufficiently, individuals may need corrective lenses or glasses. A nearsighted eye is able to see images clearly when the object is near the eye. Notice that the path of light from the source is focused nicely on the retina. But when I move the eye model far away, the focal point is in front of the retina and the image is not in focus. However, this is easily corrected by wearing glasses. If I put an additional lens in front of this eye, this lens will spread out the path of light so that the lens inside the eye is now able to focus on the retina. Now let's look at a far-sighted eye. When the source of light is far enough away, the eye focuses the image very nicely. That's why this condition is called farsightedness. But when the eye is close to the source, the lens is not able to get the image in focus. One possibility is that the lens isn't flexible enough to thicken sufficiently. This happens to all of us as we age. But using reading glasses adds the extra thickness needed to refract the light so that the eye is able to focus the light on the retina.
Dr. Sittick and Dr. Wainwright showed us how light enters the eye and reaches the retina, producing an inverted image. As we've seen, the camera is a good analogy to the eye. Here we see that light from an object is refracted by the lens in such a way that the image on the film is inverted. Of course, we don't actually see the image on the film until it has gone through a chemical process known as developing. Earlier, we heard children accurately describing an inverted image of an object on the retina. But just like camera film, we don't see an image on the retina. Instead, light is absorbed by the detectors on the retina, transformed into chemical energy, which initiates messages in the optic nerve that go to the brain. So we might say the brain develops the picture. In classrooms, children can explore image formation using hand lenses. We visited children from Linda Holland's combination 3rd and 4th grade class in Lowell, Massachusetts, to watch their explorations.
Hey, go. Can I see yours?
You're here.
Children are familiar with the use of hand lenses to produce a magnified image of the object they're examining.
But when you look on the top, it looks like a bunch of mountains.
But if the object is far away from the hand lens, they can capture an image on a screen, such as a white piece of paper. Here we see the children produce an image of the trees that they see through the window. The image is upside down. The lens of the eye works in a similar way to this hand lens, inverting the light that lands on the retina.
I can see outside and I can see the window.
Here's a simple model that shows how the eye works. We use a clear plastic dome for the cornea, some construction paper and paper fasteners for the pupil and iris. We use a plastic hand lens for the lens of the eye, and water in a clear plastic container with a little yellow dye added as the liquid in the eye. At the very back of the model, where the retina of the eye would be, we place a piece of mounted paper. Looking at the model from above, we can see the path that the light takes through the lens, the liquid in the eye, and onto the retina. We can clearly see the inverted image of the light bulb on the retina. When we open and close the iris, we can see the difference in the amount of light falling onto the retina.
Let's return now to Dr. Sittick and Dr. Wainwright as they look at the retina, the place where the light detectors are found.
Dr. Sittick, tell me about the detectors on the retina at the back of the eyeball.
Those photoreceptors that we're looking at, they're rods and cones. Rods give us our nighttime vision so that we can see in low light levels, but it's not very clear vision. Also, there's only one type of rod, so the only information that we get is about brightness. We can see different shades of light and dark, but we cannot distinguish color. When the light level gets bright enough, then the cones start to work. And when the cones work, the rods shut off. You know that your cones are working when you can see color because we have 3 different types of cones. One type is sensitive to low energy photons, another type is sensitive to high energy photons, and one type in between is sensitive to the middle energy photons. When those are working properly, they give us color information. The ones that respond mainly to the low energy photons see mostly red, but they do respond to other colors as well. The ones that have the peak sensitivity in the medium energy, those respond mostly to green, but again, they do see other colors as well. And then this final curve where they respond mostly to the high energy, those have the peak sensitivity in the blue region of the spectrum, but as with the others, they do respond to all colors.
I'm surprised to hear that. I usually think of them as corresponding strictly to the red region and the green and the blue, but you're describing it as a much broader spectral response than that.
Yes, it is much broader. They do have peak sensitivities in the red, green, and blue parts of the spectrum, but they do have sensitivity across the whole spectrum.
And those that respond to the low and the medium energy photons are really pretty close together in their sensitivity.
Yeah, those sensitivities are fairly close. And when someone is color deficient, what happens sometimes is that those peak sensitivities are closer together than they should be. So even though that person has all the cones, it's harder for that person to discriminate colors.
I see. So I suppose that if someone were colorblind, it would be because one or more of those types of cones isn't functioning.
That's correct, but we prefer the term color deficient, because even though someone is colorblind, they can still see color, they just cannot distinguish certain types of colors. Usually what happens with males, because it's more common in males, is to have difficulty discriminating red from green, and those would be the low energy and the middle energy sensitive cones. Now, we said there was only one type of rod, but we can see at lower light levels with the rods.
So that would explain why in low light or in the evening we're not able to see color, but we might be able to discriminate light and dark because the rods are so sensitive.
Yes, that's correct.
So it sounds as though there's an analogy between the rods and black and white film in a camera and cones and color film.
Yes, that's actually a very good analogy.
Now we know that seeing color is really the result of cones receiving energy from photons with different energies. Photons themselves have no color. But are there colors that are easier to perceive than others? Let's see if we can find out. In this demonstration, we placed 3 colored filters on 3 desk lamps: red, green, and blue. Each lamp is connected to a dimmer. We shine each color onto a piece of white paper, making sure that all of the lights are at full intensity. Which color looks brightest to you? Our eyes perceive green to be the brightest, followed by red, then blue. We adjust the dimmer level of each lamp so that they appear to our eyes to be of equal intensity. Notice that now the green dimmer is lower than the red, while the blue is at full power. Our eyes are most sensitive to green light and least sensitive to blue light. You may have noticed that many emergency vehicles, like fire trucks and ambulances, are now painted yellow or green. This is because the human eye has its peak sensitivity in the yellow to green range. And that's not all of the visual information the eye has to interpret. From all the signals the brain is receiving from the eyes, it must interpret distance, movement, size, and color.
The brain processes a vast amount of information received from the eyes. But during this processing, the brain groups the information it receives into patterns that are sometimes incorrect. The result is an optical illusion. Artists have made use of the visual processing capabilities of the brain in their work. Pointillists such as Seurat produce paintings using thousands of tiny colored dots. When two different colored dots are right next to each other, your brain mixes them together with the effect that the dots are not distinguishable unless the viewer is close to the painting. Let's return to Michelle Sullivan's 4th grade class, where they've been doing some pointillist drawings of their own.
Boys and girls, remember that when you write your prediction, it's what do you think it will look like from across the room? What color will you see from across the room? You tell me. What does it say? Your prediction was correct, and then write down what you actually saw, okay? While you're waiting, if I were you, I might add a couple more magenta dots in the middle because that might give you a different color. When you look at it from far away, you might want a few inside. Magenta? No, put dots in. Yeah, you can sit for a few minutes.
Say 20 or 30 or whatever, blue dot, and then you did double them.
Oh, nice job, girls. What do you see here, Joseph? Orange. Did you think it would be orange? You wrote cyan. So were you surprised? What about when you mixed your colors together and you wrote your predictions, some of you were really surprised. I heard you say, oh, wow, when you were standing across the room from each other. How many of you had a different prediction than what you actually saw? Chris, what did you get?
I thought it would be blue because yellow doesn't show up as well as blue does.
Right.
So I thought it would be blue. But when I did the experiment, it turned out as a light green.
Can we see your paper? Oh, you're absolutely right.
How does it like make a different color?
Marina?
Because it kind of blends in together, and so you see it.
Right. What color does Marina's look like? Christina?
Green.
It looks green to me too. Who says that looks green, the third one? Okay, good, nice job.
What happened if that went into the Get in yellow. I'm trying to make a red for the lips and the signs on his hat.
I tried to get the color brown for the stem, and I used red, blue, and green, and like.
Okay. Okay, Sonia?
I'm trying to get the red orange with. You put yellow in that blue, and you get the brown. For the purple, you put purple.
I did a butterfly, and I put little holes in, like little circles, and in the circles I wanted it to come out green and purple, or violet. This came out green when I mixed blue and yellow together, but this kind of came out like a purple and a blue. Over here in the middle, I tried to make it brown, and I thought that magenta and black would make it brown because it looked like it in the paper. I used magenta, cyan, and yellow for the stem, and that makes brown if you combine them all. I used yellow and cyan for the leaf to make green, and I used magenta for the apple. I made a flower, and overlapped most of the dots, and I used yellow and cyan for the leaves, and magenta and yellow for the petals, and I used yellow for the pollen.
I drew a tree, and right here I used blue and yellow. I was trying to make wind, and right on the track, and I used yellow and magenta, and I was trying to make brown, and then I did the same, at the branch I did the same thing, and right here I did the same thing with the leaves.
Great job, you guys. Very well done.
Although humans' eyes respond to the light in the visible region, there are animals whose eyes are able to detect either infrared or ultraviolet light. And nocturnal animals have eyes containing many rods for good vision in low light. And have you noticed the placement of eyes of chameleons or zebra or birds of prey? Although humans perceive many hues of color, do animals? We visited the Franklin Park Zoo in Boston, Massachusetts, and talked with the staff about how some of the animals see.
As you walk around the zoo, and those of us who take care of the critters always notice eye placement's critical. This is an example of a prey species. Every animal's a predator, is predator and prey in some form, but what these guys prey on doesn't move. It's grass and foliage. You can notice that their eyes are on their sides. This is a species which needs great peripheral vision. Their eye actually bulges out a bit, in fact, and as you notice the live specimens, you'll see how that actually works. They have a great view around their body. This is a gorilla skull that gives you an example of eye placement very similar to our own. They're in front. They have excellent binocular vision, so that if they are climbing from branch to branch or jumping from branch to branch, and they're not going to fall off, it also gives them the ability to really interpret things close up. This is an example of a predator. This is a lion skull, and you can see the way that the eyes are placed, again, in front of the head. They'll have great binocular vision, great depth perception, but they won't have as wide a view as those prey items. Their eyes are placed towards the front of their head so that they'll know when to time their leap onto their prey.
Chameleons are completely diurnal. That means they're active in the daytime and not at night. And also color is very important to them, and colors are something that's very hard to pick up at night. So their vision is strictly geared towards daytime seeing full color. These two large domes that surround the eyes, those actually allow the animal to operate its eyes independently of each other. The left eye can look off in one direction while the right eye is looking in another direction. And they are also able to take both eyes and focus them towards the front and get an overlapping field of vision, which gives them that high stereoscopic vision, which is so important to them.
Thelma is a great horned owl. A great horned owl is a bird of prey, and being a bird of prey, she has binocular vision. We think that owls are more or less colorblind. Thelma would have more rods because cones are the things that help us perceive color. And since Thelma is active at night, she wouldn't need those. In fact, Thelma could see by the light of just one candle if it were held 4 football fields away on a totally dark night.
A lot of invertebrates or insects can actually see infrared. It's something that when we look around, we don't even know it's out there, but there's infrared and there's ultraviolet light that is active in our environment. It provides another means for these insects to find food sources. Animals' eyes have evolved to meet the needs of their interpretation of their environment.
Today we looked into our eyes, literally. We see because light is reflected from objects into our eyes. The optical components of our eyes refract the light so that we see things in focus. We illustrated how detectors in our retina absorb light, which allows us to perceive all hues of color as well as black and white. It is clear that our eyes detect the light, and in conjunction with the brain, we are able to see. Next time, we'll look at how plants interact with light.
See you then.
Don't forget to check out our website for additional information, activities, and discussions with your colleagues. The address is www.lerner.org/channel/workshops/shedding-light. And if you don't have access to the web, you can share your thoughts with us by email, fax, or regular mail. Our email address is channel@lerner.org, and our fax number is 617-496-7670. Finally, our mailing address is the Annenberg CPB Channel, Smithsonian Astrophysical Observatory, 60 Garden Street, Mail Stop 82, Cambridge, Massachusetts, 02138.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.lerner.org.